Yes, please. All right. Thanks, everybody. And I hope in the next few minutes there are still some people who could join us, but I think I will just start now. Welcome to the this month's JETZON call. JETZON is the, I have to read it, joint exploration of the Twilight Zone Ocean Network. And it was formed in 2019 on one of the workshops, and of lots of programs and projects came together this workshop in the UK, and we thought, oh, why not, setting up this network and collaborate more, and discover synergies and collaborate more. But then also we have these monthly JETZON calls. One in the European time zone is usually organized by Adrian Martin, who's in the UK, and one in the more Pacific time zone, which is organized by myself, or if I'm not there, by Katie, who's kindly replacing me sometimes. And today we are very lucky that we have two amazing speakers. And first we have Claude from China, and I'd let you introduce yourself because I think that's easy.
Okay. Okay.
Off you go.
Yeah. Okay. Hello, ladies and gentlemen. This is Claude Li from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. It is my great pleasure to give this talk to JETZON. My topic is to introduce to you about an underwater camera, which we call it IPP. It is an abbreviation of Imaging Plankton Probe and related AI technologies for in situ observation of marine plankton and particles. Actually, by training, I am not a plankton guy. I'm not a biologist or ecologist. I'm a physicist and optical engineer. My research interests include developing new optical methods and turn the methods into advanced instruments. And in recent years, I'm also very interested in computer vision and machine learning. And the development of IPP was actually from the needs of our local coastal monitoring. We locate in Shenzhen, the central cosmopolitan of the Great Bay Area, which is just neighboring to the north of Hong Kong and has 22 million residents. This is a very, very large city. The city has a network of at least 13 buoys, surface buoys, which were equipped with various in situ sensors, such as chlorophyll A, salinity, and temperature. But this is not enough, of course, since nowadays the city coast also has problems of frequently like red tides and needs for monitoring coral reef sporing. Therefore, this stimulates our interests to develop a new buoy-borne plankton sensor to satisfy such demands. We choose to use the principle of snapshot dark field macroscopy for the sensor, microphotography actually, for the sensor, which is known to have good imaging performance in terms of resolution and contrast. We then designed its optomechanics, as shown on the right. We adopted a patented orthogonal shadowless laminar white light illumination to further improve the imaging quality. And we also equipped UVC radiation optics for optical window anti-fouling and embedded GPU for onboard processing and telecommunication. As the sensor is mainly used at the sea surface, its pressure rating was set to 100 meters depth. IPP takes a different illumination design from the conventional so-called oblique hollow cone scheme often used by other dark field plankton cameras, which is actually a simple duplicate of laboratory dark field microscope illuminator. This design has an obvious drawback when used in seawater for plankton imaging. That is, the spaces outside the imaging volume will be illuminated. Sorry. This will lead to problems. The first is the particles in these spaces will scatter stray light to contribute to image background noise. This becomes serious when the seawater stability is high. And the second problem is if we use white light for color imaging, the escaped light becomes beams. The escaped light beams will attract many zooplankton at night due to phototaxis. And here shows our proof. Yeah. And the first problem will cause the degradation of quality. And we defined a index called high quality image yield, which means the clear images number over the total raw images number. The second problem will cause error or even make it impossible to measure plankton abundance or any measurement. So we designed to compress the white light LED light illumination to spatially match the depth of field and the field of view of the imaging optics, like this shows, such that the illumination on spaces outside this region is minimized. And this has successfully improved the acquired quality image yield and also greatly reduced the phototaxis-induced zooplankton aggregation phenomena. The principle of IPP for plankton quantification is the same as other imagers. For any one raw image captured by it corresponds to an imaging volume defined by the product of the imaging field of view and the depth of field. So we can obtain the total sampling volume by multiplying the single frame volume with the total image number. Once we can detect and count the number of all the targets in all these frames, we can estimate the abundance by simply dividing this total number with the total volume of the seawater. We carried out several coastal raft trials of IPP before we tried on a real buoy. And then we obtained millions of high-quality images as shown here. In the same time, we developed a two-stage cascaded workflow to annotate the images and train machine classifiers iteratively via technology called active learning. In brief, we firstly train VGGNet 11 network to classify all the raw images into three classes of plankton, particles, and bubbles. Then the plankton images will be further labeled and used to train a ResNet 18 network for subclassify all the plankton. The human annotation was involved iteratively in the process so that both the construction of image database and the training of the machine classifiers are performed simultaneously. Through the group effort by student amateurs and plankton experts, we finally construct the first in situ plankton image dataset of China, named PYB PlanktonNet, and made it open accessible to the academia on IEEE Dataport. It has more than 90 classes of more than 45,000 of plankton and particle images. Here shows the image composition. The two CNNs have also achieved better than 90% performance in accuracy, precision, recall, and F1 score on the closed dataset. IPP has shown excellent anti-fouling performance during its buoy trial, as we have taken several anti-fouling actions, including UVC radiation, titanium oxide coating, and underwater wiper, like this video shows, for its optical windows, and a natural product-based anti-fouling paint for its housing. You can see after 140 days deployment, the housing and the optical window were all kept very clean. In contrast, the buoy body and the instrument protection frame were severely fouled as they were not protected. Please note that the deployment is at the subtropical sea area from summer to late autumn. It proves that our actions were very effective and successful. IPP has successfully captured many new plankton images under the buoy. You can see some key species related with ecological issues like Phylcyst globosa, jelly, Orchopleura with its house, this guy, Noctilucas, and so on. And many behavior like this arrowworm has a copepod inside and some mating behavior. We can also see many plankton behaviors like this predation, mating, and etc. With this buoy data, we could obtain months of time series of overall particle and plankton abundance, as well as dominant species variations. The fine time resolution offered by IPP can also easily make us see the plankton vertical dial migration phenomenon. This is data from 1 week. It happened a so-called crisis acicula breakout event was also recorded. You can see. Let me show you the short video. Yeah. Now, this is the only record in history of this sea area, which threatened the safety of nearby nuclear power plant. The abundance statistics estimated from IPP data was inconsistent with another team using traditional net sampling and manual counting. Like many other known in situ instruments, IPP has also evolved from its very prototype to new versions since its birth 6 years ago. Now it becomes smaller, lighter, and more mature. Our institute spin off a company called X-Cube Tech, dedicated to make it from a usable research tool to a useful instrument product for more users. This is the latest specification, and note that it has 2 magnifications supporting 2 sizing ranges. Its average power consumption is just 15 watts, which is quite compatible for many platforms besides the buoy. Actually, we also developed many AI technologies to further strengthen this instrument. Because for any underwater plankton imagers, it will inevitably encounter the following imaging quality degradation problems. The first is when we use low magnification for larger observing more seawater in unit time, we'll have insufficient resolution. If we switch to use red or near-infrared light to completely eliminate phototaxis issues, we will lose image colors. The third one is even we have compressed the illumination, we can hardly avoid the space outside the imaging volume being illuminated, and hence out of focus blur could always exist in the captured images. And our idea is to use data-driven algorithms to restore the image quality from low resolution to high resolution, from colorless to colorized, and from defocused and infocused. And this slide shows the so-called is plankton SR. We give a name. It is an image super resolution algorithm effect. We used computer vision metrics as well as optical calibration standards to evaluate its performance. It proved that from 1.59 times to 2.82 times resolution improvements, resolution improvements for the ×2 or ×4 race channels. Also, we confirmed that the image captured by our instrument, the algorithm also apply for images captured by other instruments. And the second one is grayscale image colorization, and we call it is plankton CLR. It can help us to convert grayscale images into color to its natural colors. Now the algorithm can generalize to a long list of plankton groups in the DYB PlanktonNet dataset. This work has recently been published in ECCV, which is the top computer vision conferences. The third one is called Is Plankton FE, and this paper has just been published in March, which can help to refocus the blurred images into sharp images. Is equivalent to extend depth of field of IBP to 7 times. And to our surprise, the algorithm also generalized quite well on particles. Although we did not use any particles data to train the AI. This will potentially expand the application of IBP for research topics such as particulate carbon cycling studies. And we also develop image recognition algorithms. Here is plankton image retrieval. And this is a framework to show how it works. And we build a gallery, and then for all the new images, the AI will extract their features and compare the similarity between an image with the other images inside this gallery. And depends on the similarity, it will rank all the images, and the most similar guy will be selected as the recognition results. Well, the idea sounds simple, but to our surprise, almost all the publications so far, they never use this framework. And this framework will bring us a lot of flexibility for engineering application for such algorithm, because we can simply build a gallery and let the users to freely adjust this gallery. Then the AI should not be, there's no need to retrain the AI very frequently. That will save cost and time. And here is the project between us and Ruth and Anthony with Cyril, located in Cyril, Hobart. We call it AI Plankton. Actually, AI in Chinese, the pronunciation of AI in Chinese is just equivalent to love. Okay, I love you in Chinese pronounce 我爱你, 我 means I, and 你 means you, and love, yeah. And the idea is we'll develop 8 IPPs and deploy 6 in the coast of China, especially to the south and east coast of China. And we'll also try to develop 2 in Australia. Yeah, maybe Hobart and maybe some other locations. And we'll visit Ruth in June. And the aim of this visit is to identify the best sites for deployment. And then all these IPPs will be networked by the telecommunication network, and we'll run the AI algorithm on the cloud. And then we provide a platform for users to log in from anywhere. That's the simple idea. And in China, we have done very hard work, and we have deployed 4, but only 2 have been connected. The other 2, we are waiting for the weather. We are waiting for the temperature in Dongshan T-Smart Station, which is a coastal observatory of Xiamen University. And Xiamen University ranks top in marine environmental science and ecology science in China. And here shows some of our images. So finally, let me give you some technical message. And we have successfully developed a new underwater plankton imager. And this imager can support under buoy deployment and wireless communication. So that means all the small images will be transferred back instantly as long as they are captured. And we developed AI for plankton image labeling and classification. So long time for plankton abundance and behavior were observed. And we also developed some new data-driven AI algorithms and we will try to implement them on the real camera and as well as the system. So finally, I would like to acknowledge all my collaborators from universities, from CSIRO, from some companies and local NGOs. And this is a picture of Shenzhen coast, and you are welcome to visit us, which is also beautiful. And you can easily fly to Hong Kong and take high-speed train from downtown Hong Kong to Shenzhen downtown. It takes only 19 minutes. Yeah, thank you.
Thank you so much. That was amazing. I can't even, yeah, it's amazing. So if people have questions, either put them in the chat or raise your hand or just speak up. I think we're in a small enough call that you can just speak up. I guess while people thinking about questions, the idea for this observing system is you kind of, for example, you detect an algae bloom kind of potentially harmful. How fast would it take to detect that? You know, you have those out and then the data gets transferred back instantly, but how long does it take for you to react, basically?
Let me try to answer this question.
Maybe a bit early in the process, but
I better go back to these specs. As you can see, IPP is not that good at imaging phytoplankton, single cellular phytoplankton cells, because it is still a camera, not a microscope. So the sizing range is from, actually, we can actually detect the smallest around 200 micron if they are identifiable. So within this range, Noctilucas should be no problem, and those Phyllis globosa, no problem, because they will grow into colonies very big. And for other HAB, which is not to the advantages of IPP, but this is also very challenging for any in situ phytoplankton imager. That's because we are restricted by the law of optics. Because if you are chasing for resolution, you will lose your field of view and depth of field. If we put into seawater a very high magnification lens, it's supposed that the water volume that you can sample is very, very small. So even it continuously work underwater, the seawater volume sampled in unit time, in my eyes, it is not representative enough to reflect the seawater condition. But our camera will, it works underwater. It captures full frame images at a rate of 4 frames per second. That means in every second, it will take 4 very big images, and the computer embedded inside the instrument will do pre-processing instantly. It will detect the targets and only crop the small targets and send them back as very small images. And this process is almost instant, which means once I capture the image will be sent back to a server. And then if we can run some algorithm to monitor the trend from the history to the present, and we can work together with some modelers. And I think that will bring very instant data to these modelers. And that's why we collaborate with CSIRO and also some Chinese scholars and collaborators to further develop this technology.
Thank you so much. Maura, I think you are next.
Yeah, I was just curious how long you can leave that out. Like if you wanted to put it on a mooring that you couldn't service that often. I mean, you talked about anti-fouling. So yeah, I was just curious how long you could leave it. Or could you leave it in Antarctica, you know, and go away for a year and continue to get real-time data?
Very good question. The most challenging problem is biofouling actually. For energy supply and other like data telecommunication, at least in coastal areas in China, our wireless communication network is very strong. We have 5G network. The bandwidth is not an issue. So the biggest headache is fouling. And we take several actions as I introduced. And here you can see after 140 days deployment. And since this deployment, we have tried IPP in many places, at least 6. And the longest record is 7 months without any human intervention. We used to deploy it near a water intake of a nuclear power plant and in Hainan province. And the IPP worked there for 7 months. And our target is at least in coastal areas, we should make the maintenance free time to be more than 3 months.
Ruth asked, how precisely can IPP measure wire volume, for example, looking for changes in Phaeocystis colony size over time?
We haven't tried because Ruth has not been able to access to IPP. We are figuring how to ship IPP to Australia now. And so that's the purpose of our visit next June.
Awesome. All right. Is there anybody else has another question maybe? Otherwise, we probably move on to Maura. Thank you so much for presenting. It's amazing. It's